are going to define similarity based on transformations. Now, just so you know, I have taught similarity before. I have taught about transformations before, but this is a new concept for me, is bringing the two together. And we're going to define similarity based on a transformation. Okay? And I think I went over that other paper with you the other day about it. I did. So we're going to go right here. I would like someone quickly, who would like to read the first 3 paragraphs for us? Volunteers? All right, Andrea. Andrea, you got to stand up and turn around. Your voice is kind of soft.
Similarity transformation is a transformation in which the image has the same shape as the pre-image. Specifically, the similarity transformations are the rigid motions, reflections, translations, and rotations,
okay.
as well as dilations.
Okay, stop right there. Okay, hey, you guys. You have talked about these transformations before. Did we write these down the other day? You guys learned ways to move things last year. What are those 3 ways? Reflections, translations, and rotations, right? And what were the other names for these? What's the other name for reflection? Flip. For a translation. Whoa. And a rotation. Huh? Turns. Okay? Those are the 3 names. Then we learned a new one the other day. What was the new one? They don't have another name for dilation. It's just a dilation. Okay? Well, you can call it a shrink or an expansion. Okay? Those are some other names that we use for them. Okay, Andrea, go ahead.
2 plane figures are similar if and only if one can be obtained from the other by similarity transformations. This is by a sequence of reflections, translations, rotations, and or dilations.
Okay, put a star by that paragraph, everybody. That's what we are doing. That paragraph embodies what we are doing, okay? We are going to take a figure, and we are going to make a similar figure to it by doing at least a dilation and then at least one other of the reflections or translation or rotation, okay? That's what we'll be doing. Okay, last paragraph.
Simple or similar is the little.
Okay, everybody got this? If you have 2 triangles that are similar, let's say ABC is similar if you have triangle ABC is similar to triangle DEF, you would use that symbol in between them to say it's similar. By the way, what is the symbol for congruent? You guys, what's the symbol for congruent? 2 of those lines with a little, yeah, an equal sign with a little squiggly mark over it. That's congruent. What does congruent mean? Yeah. Yep, they're exact same shape or size. They're equal. Okay? All right, finish it, Andrea.
As congruency, it is customary to write a similarity statement so that corresponding vertices of the figure are listed in the same order.
Stop right there. Hey, you guys, this is very important to know similarity. If we write a congruent statement like this one right here, that means A and D are going to be congruent. Because remember, the angles are congruent on similar figures, but the sides are not congruent. They're proportional. That means B and E correspond because they're written second, and C and F correspond because they're written third. Do you understand that concept? Okay. We're saying that they're congruent and that they line up. Okay. So the angles are going to be congruent, and we write them in the order. So A corresponds to D. So if we could write that angle A is congruent to angle D, right? Angle B is congruent to angle what? E. Could I say angle B is congruent to angle F? No, we don't know that. Angle C is congruent to angle F. Okay? Now, I could write this as well. Segment AB is similar to segment what, you guys? DE. Does everybody understand that? What's the other two similarity statements I can write about sides? Yeah, BE, or no, BC is similar to EF. What's the last one? A what? AC is similar to DF. Is that supposed to be an F? Okay. All right, go ahead, finish.
In the figure below, triangle A prime B prime C prime is an image of triangle ABC after a dilation with center O and scale factor 2. Since the dilation is a similarity transformation, the two triangles are similar, and you can write triangle ABC is similar to triangle A prime B prime C prime.
Thank you. Okay. Any questions on any of that information? Okay, number 1A, explain why congruence can be considered a special case of similarity. Because they're the same shape. Are the sides proportional? They're not only proportional, they're congruent, right? But you can say that they're similar. So two congruent figures are basically, you can say they're similar as well, okay? Give you a second to write something down there. Write it in your own words. Okay, go on to 1B after that. Answer that question. If you know that two figures are similar, can you conclude that corresponding angles are congruent? Why or why not? What do you think? What did we just talk about here? If these two are similar, we just showed that the angles are congruent because the angles are what make it the same shape, right? The proportional sides are what makes it the same, or is what makes it similar after that. Okay, 1C, given that triangle RST is similar to triangle R prime S prime T prime, can you include that RS is congruent to R prime S prime? Why not, Audrey? Doesn't necessarily mean the sides are congruent, right? It could be if the two figures are exactly the same, but it means that the sides are proportional, right? But it doesn't mean they're necessarily congruent. Okay, go to the next page where it has example 2. Okay. Use the definition of similarity in terms of similarity transformations. Everybody underline the word similarity transformations. To determine whether the two figures are similar, explain your answer. Okay, A says triangle JKL and triangle MNP have different angles. Thanks, Daryl. Okay, so since similarity transformations preserve angle measure, what do you think about this figure off to the right, you guys? They are not similar. Why not? They don't even look the same, right? They don't have the same angles. That's what you're right. Therefore, they are not similar, right? All right, now, you guys, in this next one, R, T, and S are right here. And this is called R, I'm going to go R, S, T. Then you have another one that's here, here, and here. And this one's called X, Y, and Z. Now it says you can map triangle RST to triangle XYZ by the dilation that has the coordinate notation what? How do you write the coordinate notation? This is how you do it right here. Okay? By the way, all it is a dilation. Notice that there's no sliding it or anything. If I just dilate the small one, the RST, if I dilate it by a certain factor, it will become the green one. What factor do I have to dilate it by? Look again. It's not 2. It's not 2. Who said 3? Alex. That's right. Okay. Okay, why 3, Alex? Why 3? Okay, so you can look at it that way. You can even look at it from point to point, you guys. Let's do this right here. I want you to write point R is at 0, 1, right? And it translates, it goes to where? To point X, which is at what? 0, 3. Now, if you use the scale factor of 3, and you times each one of these coordinates by 3, what's 0 times 3? 0. What's 3 times 1? You'd get those coordinates right there, 0, 3. Does that make sense? This is the interval notation. Okay? Let's do S to Y. S is at where? And it goes to Y, which is where? What do you think? How many of you got that one right there? 1, -1 to 3, -3. Okay, good. Let's do the last one. T to Z. Where would T go? T to Z. Where's T located? And it goes to where? Now, you guys, everybody write down scale factor of 3. And you can take every one of these numbers, these coordinates right here, and times them by 3, and how you get those right over there. Does that make sense? Okay, any questions there? This is coordinate notation right here. This is what you write. Yeah. No, you don't necessarily. I'd like you to. I wish they would have asked more questions on this. I wish they would have asked, what is the scale factor that takes it from one to the other, and what is the coordinate notation? And then it says a dilation is a similarity transformation. Therefore, what? Are these two figures similar? I'm going to write down in that blank. No, therefore, triangle RST is what? Similar to triangle X, Y, Z. That's what you're going to write right there. Okay? So we were able to transform this, the red one, to the green one by doing a dilation. So we only needed one transformation to do it. Okay, the next example is going to take 2 transformations. What 2 transformations do you guys see? Look up on this on the next one. Okay, reflection is one of them. What's the other one? And a dilation. Does it matter which order you do them in? Okay, it does not. Okay, so I want you guys to we're going to do this one. gonna draw the picture of it first here. We have A is at 0, 0. B is at 0, 2. C is at 2, 1. And D is at 0 or 2, 0, right? And then we have E is at 0, 0. H is at 4, 0. We have G at 4, -2. And we have F at 0, -4. Okay, and so we're supposed to transform ABCD onto EFGH. Okay, we're going to write the interval notation. What do you guys want to do first, the reflection or the dilation? Which one do you want to do? Reflection? Okay, let's do the reflection first. Okay, what are we going to how are we going to reflect it? What's it going to reflect over? Where's our line of reflection? The x-axis. We're going to flip this over here. Where is it going to be? Where's ABCD going to become? B prime is going to be 0, -2. C prime is going to be 2, -1. A prime is going to be at A. And D prime is going to stay at D, right? So everybody got that? So here we go. We're going to write the coordinate notation for that. Okay? So A was at 0, 0. We did a reflection, and A prime was where? 0, 0, right? Okay. B was at 0, 2. Where's B prime? 0, -2. C is at 2, 1. And C prime is where? 2, -1. And D is where? 2, 0. And D prime is where? 2, 0. What happened to reflect it? What happened to the coordinates? The y became negative. I want everybody to write that down. The y became negative. By the way, what do you think is going to happen if we flip something over the y-axis? The x would become negative, okay? So keep that in mind. Okay, now we've got to do something to A prime, B prime, C prime, D prime. We dilate it by 2, Colby says. What do you guys think? If we dilate it by 2, are we going to have, is it going to be on E, F, G, H? Yeah. So here we go. We're going to go A prime. I'm going to use a different color here. We're going to go to A prime, which is at 0, 0. It is going to go to E, which is where? 0, 0. B prime, which is at 0, -2, is going to go to where? 0, is going to go to F, which is at 0, comma, -4. Remember, since our scale factor is 2, all we have to do is do what? Times all the A prime, B prime, C prime, D prime by 2, right? Okay, C prime is at 2, comma, -1, right? So G is going to be where? Okay, 4, comma, -2. If I times 2 by 2, I get 4. 2 by -1, I get -4. So 4, comma, -2. D prime, 2, comma, 0 is going to go to where? 4, comma, it's going to go to H, which is at 4, comma, 0. And so if I was to outline that, it's going to be right there on EFGH, right? And so we were able, so first of all, are these similar figures? Was the original ABCD similar to EFGH? Yeah, because we were able to do 2 transformations and get it, right? We have to do a reflection and a dilation. So in answer to the questions on there, we showed the coordinate notation. Now it says a dilation is a similar transformation. Therefore, what? Therefore, what are we going to put in the therefore part? ABCD is similar to EFGH. Make sure you put that on the therefore. Similar sign. Oh, for a triangle, we don't have one for quadrilaterals in general. We have them for parallelogram, but not for quadrilateral in general. So just put ABCD. You could put polygon ABCD is similar to, yeah. And then that's why I say don't do it. Just write ABCD is similar to EFGH.
You don't write like a...
No, because we don't have a symbol for general quadrilaterals. We could just use words and say quadrilateral ABCD is similar to quadrilateral EFGH, but we already know because it has 4 letters it's a quadrilateral, so we don't really need to write that. You could, yes, draw a square in front of it. Okay, what were you saying, Andrea? You could draw the shape of it if you want. Okay, that was part C, right? Okay, reflect, 2A. In part B above, how can you show that the triangles are similar using a different similarity transformation? Is there another way other than using a dilation? No, on B, the triangles. What do you think? You could slide it first and then do the dilation, yeah. Well, actually, I don't know. If you slid it first and then did the dilation, I think you'd have to slide it back. You could make it what? Yeah, you could do that. You could take XYZ and do a scale factor of what? 1/3, right? Yeah, I'm not sure what answer they want there. I mean, the only thing I can see is we could do a dilation. So that might be what they're asking, is if you could do a dilation of 1/3, do a reduction from XYZ down to RST. Okay, 2B, in part C above, does the order in which you perform the similarity transformations matter? In other words, could we, right here in this problem, could have we done the dilation first and then reflected it? We could have. That's how we did it in my other class. We did the dilation first and then reflection. So it doesn't matter which way you do it. It's going to work out, okay? You know what? We're not going to worry about the circle thing. Well, 2a,
Say skill.
we can go from the big one to the small one using a scale factor of 1/3. That's the only one we really came up with that works. And 2b, it doesn't matter whether we, on part C right there above, it didn't matter whether we did the dilation first and then the reflection. It would have been the same thing. Okay? Hey, what you need to know about circles, you guys, is that all circles are similar. We don't really need to learn about that. It's not in our curriculum, so we're going to skip that part. And we are going to go to the assignment on the back page. Now, I'm going to give you guys more directions than what they give on here, okay? It says, use the definition of similarity in terms of similarity transformations to determine whether the two figures are similar and explain your answer. When you explain your answer, if they're not similar, you guys can just explain why, okay? But if they are similar, I want you to do what we did right here. Got it? I want this right here that we did on C. Got it? I want you to do the coordinate notation to get it there. Okay? Any questions? Okay. I'm going to give you guys about 10 minutes to work on this, and then we're going to do something else. So if you don't get it done in 10 minutes, it's homework. Got it? That's just all the time I'm going to give you right now to do it. Okay, go. Okay. Let's say that I have two triangles that are similar. Let's say we know they're similar. This might not appear similar, but let's say that they are. Let's say that this side was 7, this side was 9, and this side was, let's say, 5. Okay? And let's say it had a scale factor of 2. So what would that make this side, you guys?
10.
This side. And this side. Everybody understand that? And what they're saying is the scale factor is 2. Okay? So if we found the ratio of one to the other, for example, if we took the ratio, this side right here, 10 is to 5, right? 10 is to 5 as, what else could we write? 14 is to 7 as, 18 is to 9, and they're all equal to what? 2, the scale factor. In there, they use the letter K, right? So K was equal to each one of these ratios. That means all those three ratios should be equal, and the scale factor should be, and they should equal the scale factor, right? And that's what they were showing right there. Okay, so, okay, and so when it says reflect right here, is similarity in triangle similarity is triangle similarity transitive? My eyes are bad, sorry. Is triangle similarity transitive? That is, if triangle ABC is similar to triangle DEF, and triangle DEF is similar to triangle GHK, can you conclude that triangle ABC is similar to triangle GHK? What do you think?
Yes.
Yeah. Okay. Because they all have the same angles, right? Because each of them have the same angles. So write that down really quickly. Does it have a name? The transitive property. Yes. Huh? Hurry back. You don't want to miss this next part. Okay, given that triangle RST is similar to triangle UVW, okay, this is the next page, you guys. Example 2. Given that triangle RST is similar to triangle UVW, write congruent statements for the corresponding angles and proportions for the corresponding sides. So for A, we're going to do corresponding angles listed in the same position in each triangle. We kind of did this already. So it already gave us that, well, let's do this first. Triangle RST similar to triangle UVW. Therefore, angle R is congruent to angle U. What else? Angle what? S is congruent to angle what? V. And what else? Angle T is congruent to angle W. You guys got it. Then, the sides. Coordinate spinning sides of pairs of letters in the same position in each triangle. It says UV over RS. We don't really need to put the segment symbol over it because we're talking about a distance. UV divided by RS. Now look at where UV is. UV divided by, that is not correct. UV, oh yeah, that's right. I was looking at that thinking it was my V. How's that? UV over RS is equal to what, you guys? VW over what? ST is equal to what? RT? Well, let's... Okay, UW, yep. UW over RT. Right? Corresponding sides are proportional. Okay. Everybody understand that? Any questions? Okay, reflect. Suppose the scale factor of the dilation in the sequence of similarity transformations that maps triangle RST to triangle UVW is 4. And suppose RS is equal to 8 millimeters. Explain how to find the length UV. What would we do? Yeah, times 8 times 4, right? Does everybody understand that? The scale factor is 4. And RS is 8. How do you find UV? Since you just take the scale factor, which is 4, and times it by 8, and you would get what? 32. That would make, which one did we do, UV? 32, and RS is 4, right? Equal to 8, right? I'm sorry. Wait, which one? Oh yeah, we did 8. Sorry, this side was 8. Is 4. 32 divided by 8 is 4. Okay? All right, 2B, a student identified segment RS and segment UV as a pair of corresponding sides. Okay, so RS and UV are a pair of corresponding sides, and ST and VW as a pair of corresponding sides. ST and VW as a pair of corresponding sides. The students wrote RS over UV is equal to VW over ST. Is this correct? Is this a correct proportion? Why not? Yeah, because we went from the small triangle to the big triangle, and then the big triangle to the small triangle, didn't we? Okay, you have to have, if you do RS over UV, you have to do ST over VW, right? Instead of VW over ST. Okay, does everybody got that? Does everybody, you guys not understand what we're saying? It was this proportion right here. See that one? But they had ST on the top and VW on the bottom. And you got to have the, I mean, they had it switched around one way or the other. Okay, but if you're going from the big triangle to the smaller triangle, like it is right here, big triangle to small triangle, you got to go from big triangle to small triangle down here as well. What don't you understand? Oh, well, we'll get to that in just a second. Okay, you have seen that when two triangles are similar, corresponding angles are congruent and corresponding sides are proportional. The converse is also true. That is, if you are given two triangles and you know that the corresponding angles are congruent and corresponding sides are proportional, you can conclude that the triangles are similar. As with congruence, there are some shortcuts that make it a bit easier to prove that two triangles are congruent. The most important of these known is the AA similarity criterion. Okay, put a star by the box down at the bottom. If two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. This is just a shortcut. Everybody write the word shortcut by it. This is a way of showing that two triangles are congruent by a shortcut method. In other words, if you had to figure out if two triangles are congruent, you could do the transformations like we just did in the last lesson, or you could measure two angles of one triangle and two angles of another triangle. Okay? And I want to show you guys something. How many of you have used compasses and straight edges to do constructions before? Has anybody used those before? A construction is the ancient Greeks, just so you can understand this. Ancient Greeks invented compasses because it was an easy way to draw a circle, right? They soon discovered that they could draw all kinds of things precisely with a compass. They could make hexagons with a compass. They could make equilateral triangles with a compass. And that way their artwork was more precise. And all they used, when they did this, they didn't use any other measuring tool than a compass. And they didn't use any other measuring tool than a straight edge to draw straight lines. And that's all they used. It kind of became a game to them. What could they create using a compass and a straight edge? Well, we've used, in geometry for years, we've used compasses and straight edges to teach some of the basic properties of geometry. And what we're going to do right now is I'm going to teach you guys how to construct we're going to construct a triangle. I'm not going to be able to use a whiteboard for this. I'm going to use the blackboard. And I want everybody to take your straight edge right now. And everybody, you don't have to draw the same size triangle, but I want everybody to draw a triangle. You don't want to make it massively huge, but big enough that you can work with it on the compass. If it's too small, it makes it too hard to work on the... So all you're going to do is, and it doesn't matter what size, what kind of triangle you have. It can be isosceles, it can be obtuse, it can be acute, it can be right. I just want you to do it, and I want you to label it as ABC. Like this. Okay, now what we're going to do is we're going to construct two of the angles from your first original triangle onto something else, and we're going to get similar triangles. Okay? We're going to use this AA criterion postulate, or whatever they called it on there. What I want you to do next, somewhere on your piece of paper, I want you to draw a line bigger than you have for the bottom of your triangle. So, for example, right here, and I'm going to label the left endpoint is whatever your point right here is. Mine's A, so I'm going to label this as A prime. I need a better marker. Let's see if I can find one here. Okay, that's going to be A prime. Okay, then we are going to construct an angle congruent to this one. So everybody take your compass. Now my compass does not work very well on here. This is how you can construct congruent angles. I'm going to take angle A right here, and I am going to construct an arc through angle A. I'm going to put the point of my compass on angle A, on point A, vertex A, and I'm going to construct an arc. It doesn't matter how big your arc is. Make it any size you want. Open up your compass any length you want. And then I'm going to come over on A prime and put that same exact arc. So don't change your compass setting once you do it on the first one. Got it? Now, this is the cool thing about compasses. They don't have any markings on them to measure them. I know these colorful ones do, that you guys have some of them, but a real compass doesn't. Now you're going to take your compass and you're going to open it up to the distance between where these arcs intercept your triangle sides, like that. Does everybody see this? You guys look up now, because I can't hold it forever here. You're going to open up your compass so it's that distance across. And then you're going to come over here to this one, put it on the bottom one, and you're going to mark it right up here. Put a little arc where it crosses right there. Okay? Everybody got that? So all I did, one more time in case you didn't see, I measured this distance across right here. Open up your compass, and I've transferred it over to here. I measured this distance right here, and I transferred it over here to this one. Put that measurement. Got it? What are you confused about? Did you draw your arc right here? And your arc right here? Okay, you're going to draw an arc right here, like that. Got it? With the same compass setting, you're going to come over here and draw that same arc. Got it? Okay, now you got that one? Okay, now you're going to take and you're going to measure from where they where the arc intersects that side right there, and it intersects right there. You're going to take your compass and open it up to that amount. So adjust your compass so it opens up to that amount. Got it? Open your compass up so it adjusts to that amount. You got that distance? Now transfer it over here to right there. Got it? Transfer it to right there. Okay? And you are going to now you're going to draw a line going up through that angle right there. I mean through those marks. Everybody got this? Draw a line going from A prime through that arc intersection up. Now, we're going to make this bigger. I don't know what scale factor it's going to be. We're just going to make it bigger, okay? So I just want you to make sure, okay, my line right here is this big. I'm just going to make sure it's bigger. I'm going to go over here, and I'm going to put a point right there somewhere. And I'm going to call this B prime. Is my A prime, B prime bigger than my, no, it's going to be C prime, isn't it? C prime. Is my A prime AC smaller than my A prime C prime? Okay, so just do that. So your A prime C prime is bigger than your AC. We're going to do the same thing on the other side. We're going to construct another angle. See, these two angles are congruent, aren't they? We're going to do another one from this side over here. So open up your compass. Draw an arc over here. No, it doesn't. Doesn't matter what size it is. But now once you draw that arc, this one from here has to be the same. Got it? So transfer it over there. We're going to do the same exact thing we just did. So I went to C, I put an arc. I went to C prime, I put that same exact arc. Got it? Now, open up your compass to where this arc intersects these two lines right here, and transfer it over to here, just like we did before. Create congruent angles. And draw C prime congruent to C. And you're going to make this bigger triangle. Now, what we want to know, all we did, okay, everybody look up here for a second. All we did is made two congruent angles. This angle congruent to this one, this angle congruent to this one. Did I create similar triangles? Yes, I did. Okay? All right. I want you guys to look, okay, you guys have a homework assignment. Look at page 143 where it says proof of AA similarity criterion. Everybody go right here. Really quickly. We've only got 2.5 minutes left in class. So go right here. AA similarity criterion. You are going to go to this page right here, and you're going to look through the proof of this. It's different than the proof I did. I did a construction proof. You guys are going to read through this proof to see what's different about it. Don't worry. Okay, go to the next. Oh, you know what? Oh, good. It doesn't have it on here. I thought it had the other one on here. I thought it had an SAS. Oh, I think it does have an SAS criterion, but we don't need to worry about that one. Your assignment is problems 1, 2, 3, 4 on this back page, okay? No, you guys should know how to do all of this. We just did all this, except for number 4. Don't worry about 4. Let's just do 1, 2, and 3. That's your assignment for tonight, okay? Huh? Yeah, finish that other one up if you haven't.